Okay, so good morning, and so we set up the Kepler problem last time, and so one of the constants of motion. So there were we had two constants of motion. One was the energy. Okay, so we decoupled the center of mass thing, so we are not looking at that. So this was the other one. Second one was P phi, which is equal to Lz, which is equal to mu r square phi dot. Okay, so I remember that mu was the reduced mass. Okay, and so last time I gave you, I said use, Lz is also the magnitude of L because we chose theta equal to pi by 2, right? We chose the plane to be the xy plane. So use, what were the constants I said? You use mu, k, and L to obtain length scales. Time scale, and energy scale. And I asked you to work it out. And so let's call the length scale R naught. Let's call the time scale tau T naught. And let's call the energy scale U naught. Okay. So I asked you people to work it out. So can someone give me the answer to these things?
R naught is L square upon K mu.
Okay. Someone else answer now. Other one. Thank you. T
The
naught.
time scale is L cube by K square mu.
Okay. A third person, can you give me the energy scale?
Sir, energy scale is K square mu by L square.
Okay. So and the point, so we can see that without L, we cannot construct, we cannot get these length scales. So with just mu alone, we cannot. It's very clear, right? If that were true, then we would have got something with L power 0. L is angular momentum, okay, not Lagrangian here, okay. So the key idea here is that we will, because there is natural length scales in the problem, we will switch to, we will measure, okay, so these are the natural scales, these are the only scales in the problem. So we will measure in these units. Okay, so it's like MKS units. We will measure, length in units of R naught, time scale in units of T naught, and energy in this. So we'll just define some things. We'll define R tilde, which would be R upon R naught, right? And tau, we'll call it T upon T naught, and E tilde is E upon U naught. Okay, is this clear what I'm doing? I just switched units. So R tilde, you can think of it in two ways. You can think of R tilde, tau, and E tilde as dimensionless quantities, or you can think of it as radial distance measured in units of R naught, time measured in units of tau naught, T naught, and energy in terms of unit of U naught. Okay, so we had a formula here for E. Right? So we want to, what is it we want to do? We want to measure energy in terms of E tilde. So I take this equation and divide by, what should I divide it by? U naught. So I'll get E tilde. So Okay, and this. Okay, so you see something has happened. All the all the all the factors of mu, k, l, and all have disappeared, and we got something quite nice. Is this clear? Okay, so this is the simplification. You can go back here and you know uh, when I was inexperienced as a teacher, I would say that let's work in units where mu is 1, L is 1, and and so on and so forth. And energy is some unit. I mean, K upon R naught is 1. This, if you can check, is just K upon R naught. Okay, so you work in all these where L square is 1, mu is 1, and K is 1, and then lo and behold, you will see that this right hand side will just become that. Okay, all you have to do is replace get rid of all the K's and mu's. But really, one is jumping steps, and the step one is jumping is this step. Okay, so this is what we get. Okay, so just a simple remark. In quantum mechanics, we can use H bar in place of L. Right? These are only dimensions, right? L is angular momentum, H bar is the same this thing. So in particular, if you look at U naught is, what was U naught? Mu K square by L square. So you just write it as, so U naught, another in quantum mechanics, mu K square by H bar square. Okay, so for instance, in hydrogen atom or hydrogen-like atoms, K would be Z E square. Okay. I mean, you guys would be 4 pi epsilon naught, right? And mu would be the mass of the mu should be mass of the electron. Okay. So if you put all these things in, you should get up to okay. So this would be, so if you plug that in here, get me K square will be Z square e power 4, okay, divided by okay, by the way, H bar is H upon 2 pi. And in certain parts of the country, especially Bengal and Kerala, this is called H cut. And but H cut is not understood in other parts of the world, so please don't stop using that. Okay, so you can go back and compare with the formula for Rydberg. Some of you will know it, no?
No, sir. Never heard of it.
Never heard of Rydberg? Oh, interesting. So, the hydrogen atom has some energy levels, right? So it is minus Rydberg upon n square. N is the principal quantum number, n equal to 1, 2, 3. These are the energy levels of the hydrogen atom. You haven't learned this? At least chemistry. And Rydberg is, what is the value of Rydberg? Anybody knows? In EV?
Minus 13.9 or 13. Yeah, 13.6 electrons.
Okay. So what I'm trying to say here is that the power of dimensional analysis tells you that there's only one energy scale in the problem. Whatever be the energy levels of this thing, it should be in units of U naught. I'm not saying U naught is exactly Rydberg. There might be some factors, okay? But the dependence on the parameters will be exactly as I wrote. Okay. So even if you didn't know anything, you could get that. Okay, so let's come back to our problem. And let's plot V effective. So we'll call, what is it? This is V effective. Okay, so you can work out what it is, and it has a minimum. It is V effective 1 by 2 R tilde square minus 1 by R tilde. So let's work out where its minimum is, extremum is. So you can check that. R tilde equal to 1. Okay, so I need to do a plot. So let me do that here. Okay, so let me now draw the curve. It goes to infinity, the minimum here, and then goes to. So this is a kind of thing, and let's just ask what is V effective at. It's minus half, or its value is minus half U naught. Want to put so this number here is minus half. Okay, in units of Okay, so now the thing is that we can ask what are the. So we'll consider two different energies. I'll first consider this and this. Okay, great. Okay, so let's call this E1 and we'll call this E2. Okay, we have, of course, we have a three-dimensional problem, which became a two-dimensional problem once we chose the axis properly, but this is just the radial part of the story. And so something went wrong here. Okay, so you can see, so let's consider E equal to, first thing we can see here is that so let's do some remarks. The first remark is that you cannot have energy less than minus half. So energy has to be strictly greater than or equal to minus half in units of U naught, which is the same as E tilde being minus half greater than. Right? Is this clear? Okay, because second one, E is greater than 0, particle like such as E, so that's E2 for instance. E2 is something greater than 0, which is this guy. So you can see that's one turning point. So if you send the particle towards this thing, it will come, bounce off, because it's like a barrier, you'll see the barrier and come back. So it's unbounded motion, right? Is this clear?
Yes, sir.
Okay.
Sir, in that expression of V effective, if we put R tilde equals to 1,
you get minus half.
Okay. Yeah, okay. Sorry.
That's what I wrote, minus half. So it's bounded from below so the potential V effective is the smallest value it can take is minus half. Okay. So third part is, minus half Yeah, I should call these guys E tilde, no, because the graph is also that. So let's put tildes here. Okay, so E1 is, oh, I got the directions all wrong. E1 is greater than mu naught but less than 0, which is like E1, right? So now there are two turning points. In other words, it's bounded between, so let's call this R1 and R2. Okay, so motion is bounded and R1, R is restricted to okay. Does this mean we have periodic motion? Anybody?
Not sure.
Okay, it doesn't mean, okay? But turns out for the Kepler, okay, so this is what I'm going to say, so I should say it first and then say for the Kepler problems. Bounded implies closed orbit. Okay. Not true in general for other, Okay. Suppose we have some other potential. No, we can still plot this kind of V effective like we did here, and we can talk about turning points, etc. Let's say there is something which is exactly similar to this. Okay, so then what we will see is that it doesn't happen. I mean, this doesn't happen. In a sense, you will have these turning points R1 and R2. So it will be bounded in R1 R2 space, but in the phi angle, it may, when you go from R1 to R2 and come back to R1, phi should change by one period, right? If it doesn't happen, it's not closing. Is that clear? Okay, so because it's motion in 3D. So this is what is happening. Okay, so now let's
would that be like a sudden boundary condition, like for example a wall? Is that what you mean?
No, that's not what I mean. What I mean is that in R it will go like this and come back in R. But in phi it should, during that time, it should go from 0 to 2 pi or something like that. It should come back.
Okay.
Right? Only then that means it should come back in R theta space. So what is a closed orbit? It starts at one point and goes somewhere and comes back. This is, I'm drawing in the plane, but it should come back. So this would correspond to the same value of R and theta. Theta is a phi rather. Phi is periodic. So, okay. So there is something very special about the 1 upon R potential. Okay. So I'm just cautioning you that even if we draw something else which is not 1 upon R, that's what happens. Okay. So, okay, good. Okay, so let us do some recap of Kepler. So Kepler, what is Kepler's laws? Let's first derive that. Okay, and this where the first law. What is the first law? Somebody will know this.
The planets move in elliptical orbits with the sun at one of its foci.
Foci. Okay. Correct. Second law.
The aerial velocity is constant.
And what is the third law?
T square is proportional to a cube.
This is time period of the orbit, and A is the semi-major axis, right? So if you have an ellipse and this is semi-major or semi-minor, what is it? I don't know. Okay. This is semi-major, right? Okay.
Yes, sir.
Okay, this is the focus. Okay, so these are the things. So let us try to derive them. Okay, so first thing is easy one. The second and third law are easy, second law. Okay, so what is aerial velocity?
The radius vector sweeps some area within a
So you
time
have something
interval.
like this, yeah. So you have some angle. So
d by dt of r d theta.
yeah, so phi. So it will be. I just want a formula, right? So we want r phi dot, right? R phi dot is a constant, is it? Or r square? Sorry, area should be that. So r square phi dot is a constant. Because this way, think of it as small thing. This is r theta, this is r, and for small thing angles this is 190 degrees. So r, it doesn't matter half r square theta phi dot or this thing, it is a constant. But if you go back and see what p phi lz is, it's mu, which is a constant, times r square phi dot, right? Is indeed. Okay. So is this fine? Okay, so we have proved that. Third law is also very interesting. Okay, so what we know is that whatever is t, it should be measured in units of t naught. You agree? We can measure it. Is it little? What did I use? Little t naught, no? And a, you have to divide by r naught. Okay. So what I'm trying to get at, you will see, whatever we do this way, t. So what does this mean? T will be some constant times t naught. Okay, and this is a claim. And similarly, a will be another constant times r naught. Because these are the only length scales. By a constant, I mean, so there's constants do not depend on any parameters, on say mu, k, or l, right? All that dependence is buried here. This is what it says. Right? Do you agree with what I've written, what I'm claiming here?
Yes.
Okay. Okay. Now comes the most interesting part of the story, is that both T naught, let's write out what T naught was. Again, T naught was L cubed by mu k square, and R naught is L square upon mu k. Okay, so let us look at the following combination. T naught, I will square it and divide it by R naught cubed. Something interesting happens. Okay, the powers of L cancel. Okay, and you're left with T naught square upon this thing. So T, yeah. So this is equal to mu k whole cubed divided by mu k square whole square. And this, if you just work out, is mu over k. Okay, so key observation here is that this combination does not depend on the initial conditions. Okay, so now is this clear? You see the L is the only object which depend on initial conditions. Mu and k are just some parameters which are fixed in the problem. Is this clear? L changes. You can have the same thing. If you change its L, it will give a different orbit. So this is independent of what orbit we are looking at, but it of course depends on the planet because mu is appearing, and k also depends on that. Okay. So actually, even if you go back, so let's do this. So what do we expect? So what I want to say is that T by T naught whole cubed should be proportional to this thing, A by R naught whole cubed. And what should appear here is a constant, which does not depend on mu, k or anything. Is this point clear?
So there should be a square in the left.
Yeah, somewhere one thing should be square. Which one? T should be square. Thanks. Okay. So, and this is independent of initial conditions because it doesn't depend on L. And and if you work out the constant, answer is true. But what I'm trying to say here is that this is 4 pi square, not 4 pi whole square, but 4 pi square. Okay, so exercise. Closed orbits, that means elliptic orbits, elliptic or circular. Okay, so ideally I should have done, I should have done, the first law, but somehow I felt let me do the second and third law, and now let's do because we need to do some integration, etc. So I'll pause here. Are there any questions? I mean, what I'm saying here is that if you look at this formula we cannot sit down and contemplate to infinity without a calculation and get 4 pi square. But we can, without any calculation, say that there must be some constant which is independent of mu, k, everything, etc., etc. Okay. So
we are taking as a given that time period, something like time period exists. That
So first law tells you that there are other trajectories also. I mean, if it's a planet, it's a bound. So for planets which are bound, right? Let's come back to this picture here. So these are true for planets. If something had energy like E2 or E2 tilde, those won't be bound. They can come close, they'll come to some close value and go away. Okay. So, is this clear? Okay, so it has to be so it's only true. I mean, Kepler's first law really we have to. That's why we need first law before we discuss this thing. So it's a bound state. Okay, so first law. Okay, so we need to know the trajectory of the particle. Okay, so how would we do this? So we will assume that we have r tilde as a function of phi. Okay, so we have to give this equation. So we need to work out what this would be. So what we will do is we will try to do the following thing. Okay, and so dr by dt up to a sign. So we can go back to the f. So this we know from energy. Okay, energy is a constant. You can take a square root, and phi dot we know from Lz equal to constant. Right? So both of them are known. So you can work out what this is, and that's a square root. So both possibilities exist. You can work this out. It's r tilde square. Okay. Okay, we need to do this integration, and so is it clear what I have done? So p phi will so you can trade you can write d phi by dt as some L by, so what was it, m r square, so L by r square with some factor, this will be this. So all those things will come in, and we are working in natural units, so L will become 1 and go away. So this is what you will get. Okay, so we need to integrate this thing. So what this integration we'll do by change variables. To W okay, and then you can check the dW by d phi, which is equal to minus 1 by r tilde square. I just differentiate this formula, dr tilde by d phi, and you can see there's an r tilde square multiplying this, that goes away, and we just get minus or plus square root of 2e tilde plus 2w minus w square. Okay, now we can do the integration in a formal way. Minus or plus phi plus some integration constant phi naught should be equal to integral of dw divided by square root of, there's some completing of squares going on. Okay, so this is some constant of integration. Okay, and now we can do this integration. Okay, so exercise, do the integration. Okay, and you will get one answer, which is very easy. It says W minus 1 equal to epsilon cosine of phi plus or minus phi naught. Okay, so epsilon has a name called the eccentricity. Okay, and we can rewrite this whole thing by Now going back to writing it as 1 by r, and we can write it as 1 by r equal to r naught is the length scale in the problem, 1 plus epsilon cosine phi minus phi naught. Okay, so this is the equation of what is called a conic section. Okay, so what is a conic section? You take a cone, okay, you can slice it with something like things which is like this, you'll get a circle. Do it at a slight angle, the cross section will be a ellipse. Okay, parabola and how would I get a parabola or hyperbola? Anybody?
So parallel to the
So
curve.
parallel to the curve, like this. No.
No, sir.
Perpendicular to the
Which
circle.
is parallel to that slanting line.
Like this.
Yes, sir.
Just cut in half.
Okay, so you can get open and close. So these are all conic sections because they're slices of a cone. Okay, so now I need to make a table. So let's do that. I'm not able to move it. Okay, great. Sorry, I'm not so good at all these things. Okay, so when E is equal to minus mu naught by 2, that means it's at the bottom of the potential. Epsilon, if you go back to the definition, it is 0. You get a circle. Bound state is minus mu naught by 2 less than E less than 0. This is 0 less than epsilon less than 1. Okay, I'm using the wrong epsilon here. This is ellipse. Okay, E equal to 0, epsilon equal to 1, you get a parabola. And E greater than 0, epsilon is greater than 1, and you get a hyperbola. Okay. Okay, so these are bound. So this is where first law holds or applicable. Okay, and I just want you to remember that epsilon was square root of 2 E tilde plus 1. Okay, so you can see that when E tilde is minus half, the epsilon is 0. Okay, so this concludes our discussion. So like I said, we can't always do this integration. We can come up to a step like this, but we cannot quite do the integration in this thing. But in this case, we can. Okay, so you can. At least at the very least, you can go and check that what I've written here indeed solves the equation. Okay. So in some sense, the generalized Kepler's first law, yes, trajectories are conic sections. Okay, is this clear? So we are able to make more general statement than just for the case of bound orbits. And actually, you can also, second law makes sense for everything, right? Because angular momentum, it's just a statement of angular momentum being conserved. Okay, so can also make sense of third law if one defines the analog of t and some length scale a for hyperbolic orbits. Okay, but this is a kind of baroque, very, I mean, you have to construct some t and construct some a, because if you look at the argument, we did not make use of, we just used scaling arguments, and we didn't appeal to anything else, right? Okay, so hopefully this has given you some new insights into how we can understand even Kepler's laws in our general formulation, and also it's a very nice application of all the ideas that we have used, ideas of constants of motion, that's a Lagrangian, how to use the equation of constants of motion to simplify, to solve for first order equations instead of second order equations, and so on and so forth. Okay, so I think I don't have more things to say, so I will stop here. For a change, I finished before time, so floor is open for questions.
Sir, I just wanted to confirm the syllabus for tomorrow's quiz is entire thing until now, right?